Hello, good people. This is Calculus, Early Transcendentals, and we are discussing applications of the derivative, and we are on section 4.4, L'Hopital's rule, which can be applied to calculate limits of functions that are going to 0 over 0 or infinity over infinity only. And so remember, if your function is going when you're taking that limit is tending towards infinity over infinity or 0 over 0, then you can apply the rule, and the rule of L'Hopital is that you can take the limit of your quotient is going to be the limit of the derivative of the numerator over the derivative of the denominator. And please note that that is not the quotient rule for derivatives. All right, so to date we have gone over the standard application of L'Hopital's rule. It appears within a lot of the other indeterminate forms. We had, in the last couple of videos, I presented examples of indeterminate products, which is a 0 times an infinity or a negative infinity. And in the very last video, I went over indeterminate difference of infinity minus infinity and how to approach that. And so today's video, in this one, we're going to go over indeterminate powers and how to address those. And that typically happens when we've got the limit of an expression in x or a function of x raised to another function. And when you're taking that limit as x approaches a, if that limit approaches 1 to the infinity or 0 to the 0 or infinity to the 0, we have an indeterminate power. A lot of people will believe that 1 to the infinity is still 1. They'll think that 0 to the 0 is 1 or infinity to the 0 is 1 because x to the 0 is 1 for all values of x not equal to 0. But it really is a question of, because, you know, f of x might be going to 1, but it may never actually achieve 1. G of x might be going to 0 or infinity, but it might actually not achieve that 0. So we don't, and it's a question of which one's getting there faster. So how do we address this? Well, we use the natural log. In most applications in mathematics, if you end up with an expression in x raised to another expression in x, in order to get at that exponent, it's common for you to take a natural log and use that natural log property of ln of x to the a equal to a times the ln of x. All right, so basically our overall process will be we want to calculate the limit of our function, right? And that would be an f of x to a g of x. But we're going to take the natural log of both sides. And so this would be the natural log of the limit as x approaches a of f of x to the g of x, right? And that's just going to be the limit of the ln of f of x to the g of x. And that's when we'll start applying our log properties. We'll almost always end up with that indeterminate product, in which case we can turn it into a quotient that will have L'Hopital's rule apply and continue forward. But this would be the limit of the ln of L, and we want to find L. So our final step 2 answer, so we would just continue and achieve and get this value. But our answer will be that our limit will be e to the ln of L, and that is a composition of inverse functions, and that's how we will end our calculation. All right, so let's take a look at a couple of examples and apply this technique. All right, so make sure that we are, our function is going to an indeterminate power before you proceed with this technique. So that's what I do first. And our first example is calculate the limit as x goes to 0 from the right of x to the x. So my limit as x goes to 0 from the right of x to the x is going to 0 to the 0, and that is an indeterminate power. So my step 1 is I'm going to let my L, or my we want our L to be the limit as x approaches 0 from the right of x to the x, but I'm going to take the ln of L, and that's going to be the limit as x approaches 0 from the right of the ln of x to the x, just putting that ln on the inside of that limit. Now I'm going to employ my log properties. This is equal to the limit as x approaches 0 from the right of x times the ln of x. I'm going to try to calculate my limit here, and I'm going to 0 times the ln of 0, which is going to 0 times infinity. That's my indeterminate product. And remember, what we do with indeterminate products is that we take one of those factors and put it into the denominator. And usually when I see an ln, I keep the ln inside, or on the top. And this limit as x goes to 0 from the right of this function is going to be equal to ln of x over x to the minus 1. So I just took this factor and put it downstairs. And so it becomes a negative exponent. Now I have something that's going to infinity over infinity, and we have L'Hopital's rule applies. It will always apply with that indeterminate product of 0 times infinity. All right, so if I'm going to apply L'Hopital's rule, I see that this is limit as x goes to 0 from the right. The derivative of ln of x is 1 over x, and the derivative of x to the minus 1 is minus 1 times x to the negative 2. I'm just going to clean things up, and this becomes, if I put the negative on the outside and I bring the exponent, negative exponent upstairs, I end up with the limit as x goes to 0 from the right of just negative x, right? And calculating that limit, I see that that is going to 0, all right? So what have I calculated? My ln of L is equal to 0. So my final step is to exponentiate the ln of L. So my limit L is going to be e to the ln of L, and that's e to the 0, and so my limit here is equal to 1. Okay. All right. Let's try another one. So limit as x goes to infinity of 1 plus e to the x raised to the 1 over x power. We want to check where this is going. So this limit is going to 1 plus e to the infinity over 1 over infinity, and that's going to infinity to the 0, and we determine that infinity to the 0 is an indeterminate power. So I'm going to take my limit is going to be the limit as x goes to infinity of 1 plus e to the x raised to the 1 over x. That's what I want to find, but I'm going to take the ln of L, or the limit of the ln of this function, so I can get at that exponent. And now I'm going to use my log properties again. And my log properties allows me to take that 1 over x outside, and I have ln of 1 plus e to the x. And taking my limit as x goes to infinity, I see that this is going to ln of 1 plus e to the infinity over infinity, and that is infinity over infinity, so L'Hopital's rule applies. So here I go using L'Hopital's rule, and that's going to equal the limit as x goes to infinity. The derivative of ln of 1 plus e to the x is 1 over evaluated at the inside, but then times the derivative of the inside. And then the derivative of x is just 1. So I have this limit, just to clean things up, is just e to the x over 1 plus e to the x. And that, again, if I take my limit going to infinity, that's going to infinity over infinity. And L'Hopital's rule applies again. So I'm going to take my L'Hopital's rule, and my limit as x goes to infinity The derivative of e to the x is e to the x. The derivative of 1 plus e to the x is e to the x, or 0 plus e to the x. This is equal to, if I cancel common factors in the top and bottom, that's going to be the limit as x goes to infinity of 1, and the limit of a constant is that constant. So what have I calculated? My ln of L is equal to 1. So my L is going to be e to the ln of L, because that's composition of inverse functions again, and that is e to the first power, and so my limit is equal to e. All right, so let's do these two, and then we'll call it a day. All right, so again, make sure that you do have an indeterminate power. So here I go taking my limit as n goes to infinity, and this limit is going to 1 plus 1 over infinity to infinity, and that is going to 1 to the infinity, and so I do have an indeterminate power. So my limit is going to be the limit as n goes to infinity of 1 plus 1 over n to the n. I'm going to take the ln of L, and so that's going to be the limit as n goes to the infinity of the ln of 1 plus 1 over n to the n. And I'm going to do my log properties again. Do I sound like a broken record yet? Maybe. I hope it sits and sinks in. So I'm going to use my log properties. I can take the n downstairs, and I get ln of 1 plus 1 over n. I want to see where that is going. That is going to infinity times the ln of 1 plus 1 over infinity, which is going to infinity times 0, right? Because the ln of 1 is 0. So we have an indeterminate product. And so what do we do with that indeterminate product? We take 1 downstairs, and I'm going to take the n downstairs to the denominator. And here I go with that. So this is going to equal the limit as n goes to infinity of the ln of 1 plus, and I'm going to make that a minus because I know I need to write a derivative with L'Hopital's rule. And this is going to be n to the minus 1. Now I'm going to apply, L'Hopital's rule applies, as it always does with my indeterminate products of 0 times infinity. And so here I go with that. That's going to be the limit as n goes to infinity, and the derivative of the ln is 1 over x, but this is the chain rule, so it's 1 over 1 plus evaluated at the inside, but then times the derivative of the inside. And the derivative of the inside is 0 plus negative 1 times n to the minus 2. And then the derivative of n to the minus 1 in the denominator is minus n to the minus 2 as well. I see that I've got common factors in the top and bottom. I can cancel that n to the minus 2 with that n to the minus 2 to get my limit as n goes to infinity of minus 1 over 1 plus 1 over n, right? Right, because that's all that's left in the numerator. Okay, so I'm going to take my, and I guess I still have a minus 1. This minus cancels with this minus, so I get this minus. I'm going to take my limit, and where's this going? This is going to 1 over 1 plus 1 over infinity, which is going to 1 over 1, which is 1. Good. Well, this is my ln of L is equal to 1, so my limit is going to be e to the ln of L, and that's going to be e to the 1, and that's also equal to e. Good. All right, and finally, this problem here, where's this limit going? This limit as x goes to 0 from the right of 1 plus x to the x, is going to 1 plus 0 to the 0, and that is going to 1 to the 0. That is not an indeterminate power. One to the 0 equals 1. So our limit as x approaches 0 from the right of 1 plus x to the x is just going to 1. Okay, so you can avoid doing the indeterminate power, but you could have done the indeterminate power. You could have done the limit of the ln and exponentiated. I encourage you to do so, but you should still end up with an answer of 1. All right, so hopefully you now know how to address indeterminate powers and apply L'Hopital's rule. Take care, and I'll see you in the next video.